Okay, so let's take a look at an example. So let's consider Canada's CO2 emissions. So in 2006, Canada's CO2 emissions were 572 megatons. And over the 9-year period from 2006 to 2015, Canada's CO2 emissions were decreasing at a pretty steady rate, and they decreased down to 550 megatons. So if we assume that Canada's CO2 emissions are going to decrease by a constant amount, so if we're going to assume their emissions follow a linear model, let's find a formula for Canada's CO2 emissions, C, which is going to be expressed as a function of the number of years since 2006. So one really important thing to catch in this statement is the fact that if we assume they're decreasing their emissions by a constant amount each year, this is the indication that we would want to use a linear function. And in order to find the linear model, we need 2 bits of information. So I've got 1 bit of information that says in 2006, it was 572 megatons. And then I have a second data point that says in 2015, Canada's CO2 emissions were 550 megatons. So that should be enough to construct this model. So step 1 would be to kind of read the example and first of all consider which model do you want to use. So by the text that's highlighted in green, we can see we'd want to use a linear model. Then let's take a look. For a linear model, what do I need? 2 points of data would be enough. What are the 2 points that we have here? Well, since we're measuring T as years since 2006, the red point corresponds to this one over here. So that's saying that in 2006, that would be a T value of 0. That's 0 years since 2006. The emissions were 572 megatons. And then in 2015, that corresponds to 9 years after 2006. So that would have a T value of 9. And that's where this second point comes from. So we know that 9 years after 2006, we have 550, Canada has 550 megatons of CO2 emissions. So now that we've got 2 points, the next thing that we can do is find the vertical intercept, in this case, because one of those points happens to be the vertical intercept. So we know what the parameter b is going to equal. B is going to equal 572. And the other parameter that we need for the linear model is going to be the slope m. And so that slope, remember, is going to equal the change in the output divided by the change in the input. So for example, these 2 points that we have, we'll consider this one at 0, 572 to be our T0 and like our f of T sub 0. And the second point we can consider T sub 1 and f of T sub 1. So that's going to help tell us what to plug into the formula below. So down here, when we're calculating the slope using the values that I just indicated above, we would have that f of T1, that's the 550. So that's where this comes from. The f of T0, that's the 572. And then we divide that by the change in the input. So we have the 9 minus the 0. And again, it's important that we put the coordinates of the second point first in our difference, and then we have the initial points that we're subtracting from them. So that gives me a slope in this case of minus 2.44 megatons each year. So practically speaking, this is telling me that every year, if Canada is going to decrease their emissions in this way, they're going to have to decrease their CO2 emissions by 2.44 megatons each year. And so now that we've got the slope and we have the intercept, we've got the 2 parameters that we need for our model. So we can express this now using slope-intercept form, which would give me that C is equal to B which in this case was 572, our vertical intercept, minus 2.44 t. So that was our slope. So in this case, our slope is negative, and that makes sense because Canada's CO2 emissions were decreasing. Okay, and so one last example to continue with the Canada emissions previous example. So let's just say we've got the model for Canada's CO2 emissions. If they're going to decrease their emissions at a constant rate over this period, then we found that that model would be given by C is equal to 572 minus 2.44 T. And so now that we have a model, we can use this to make some predictions. So let's say, for example, when is this model going to predict that Canada's CO2 emissions are zero, that they're going to have no emissions? So that is asking us mathematically to say for what value of t, what time is the output going to be zero? So we're going to set the output emissions, C, equal to 0, and then we're going to solve for t. So setting C equal to 0, we get the following equation, that 0 is 572 minus 2.44 t. Now I want to solve for t. So I can subtract 572 from both sides, and that gives me minus 572 is equal to minus 2.44 t. And then I can divide both sides by minus 2.44, and calculating that ratio gives me that t is about a little more than 234 years. So to summarize that result, this is saying that if Canada is going to follow this model for reducing their CO2 emissions, their CO2 emissions are going to reach 0 megatons about 234 years after 2006. So that puts us in 2240. And so you really want to be careful, obviously, in that you would never want to extrapolate your model out that far off into the future. So our model was based on data in 2006, 2015. We should probably just make predictions a little bit further out from 2015, certainly not 200 years out into the future. But we'll work with more of these linear models in class on Monday, so be sure to take the quiz in Canvas before coming to class on Monday. Have a nice weekend, everybody, and looking forward to seeing you in class on Monday.